Welcome to my talk in the SoftNet Expert Panel 1 and addressing challenges of simulation for citizen-centric systems. And my position or the issues I want to point out is the reality gap in simulation. My name is Stefan Bosse. I'm a lecturer and senior researcher at the University of Bremen in the Department of Mathematics and Computer Science, and my research work and my research areas addresses simulation, agent-based simulations, and sensor data science in general, including methods of machine learning and so on. So today I want to point out, to illuminate the issues that arises in simulation or with simulation compared to the real world. And the short message is reality is correct, but sensing is wrong. And simulation is mostly wrong, but sensing is correct. This is the ambiguity that we have between the real world and the virtual world. In the next in the talk I will use the term virtual world for simulation worlds. So this is the main point here. Reality is correct, but sensing in real world is mostly wrong, or at least distorted. And on the other hand, the simulation is mostly wrong, but the sensing in this simulation is correct. So what's the background? First of all, modeling of large-scale population-centric systems is a challenge. Sensing of population data is highly distorted by bias, noise, and varying or unknown test and sampling conditions. That means sampling distributions. And here I mean sensing in the real world, of course. Sensing real-world data, experimental data, especially population data. As well, modeling as simulation rely on reliable, representative and calibrated databases. And this is the main statement here. We need calibration. But how and what are the impact of calibration on simulation models and analytical models too? Yes, simulation is mostly oversimplified, of course, and simulation results do not match real-world developments. That means the outcome of a simulation normally can't be mapped on real-world environments. There is a significant difference, the reality gap. So, and variance, this is very important, on entity level. Here we consider entities mostly as humans, but it can be machines and other physical entities too. But here we have humans, and variance on the human entity level is not covered correctly by modeling and simulation, but has a significant impact on the system level outcome, the emergence. So the position is machine learning as a tool can, but must not, improve modeling and simulation of citizen-centric systems, especially considering population data and the sampling of and sensing of population data using, for example, mobile crowd sensing. Machine learning can be used to create synthetic augmented data. This is very important both for real-world modeling and modeling in simulation, or creating simulation models that match reality. So, and finally, digital twin methodologies can close the gap between real and simulation worlds by introducing variance in the behavior of the entities typically interacting in simulation. So, here a short introduction. We have two worlds colliding, real world and the simulation world. First of all, sensing in the real world. Modeling is typically the process of abstraction of large-scale multi-entity systems. So we have a model with an input vector variable x that maps on an output variable y. And finally, we can have an inverse modeling, subscript -1, that maps the opposite way. The output variable is now the input variable. That means typically the system level aggregate variables. For example, in disease monitoring, it's infection case or infection case rate, and we want to map this infection case rate to some population parameters or citizen crowd parameters like mobility, like social interaction, any kind of protection, and so on. Then we have data-driven modeling of real-world systems that requires planned and participatory experiments delivering aggregated data and or sampling of population and entity data. That means participatory or opportunistic ad hoc surveys, sensing, and so on, or experiments. Yeah, and finally, sensing of real-world data can be highly distorted by bias, preferences, for example, politically influenced preferences, socially influenced preferences, wrong a priori knowledge, and so on. Sampling strategy and sampling distributions play an important role. I will show an example where the sampling strategy and the sampling distribution is firstly unknown and secondly varying over time significantly. Yeah, and random and systematic errors, of course, statistics, small n, small number of experiments or small number n of cases. This is typically a case in sampling and population data. If you consider a distribution over horizontal, vertically distribution, for example, the distribution of the age of persons. And finally, distortion both in longitudinal, that means horizontal time, and spatial vertical dimension is a real issue. So, in simulation, if there is no closed model M that can be derived analytically, simulation can be used to study the effect of X on Y, but not Y on X. This is not cannot directly inferred. Test and probing replaces functional modeling, that means approximation by measurement. The simulation is typically another abstraction of complex worlds. A simulation model, called here S, typically bases on a large number of interacting entities, small s, E. For example, cells in a cellular automata, agents in agent-based simulation, finite element methods in mechanical engineering, and so on. So we have a set of entities, a large set of entities that provides a simulation model. And yeah, the entity behavior model is typically parameterized too. And that means each entity, each human, for example, have a specific behavior parameter set. That means social interaction, mobility, and so on, creating parameterized behavior classes. This is a generalization. That means we can merge or group specific entities, specific humans, or specific agents in a simulation to a specific normalized class. But this is a pitfall. Already mentioned, the missing variance in a simulation leads to increasing gap between simulation results and reality, observations and reality. Yeah, and finally, the simulation world, that means the spatial context, number of entities and partitions, is parameterized too. That means the world has a parameter set PV, for example. Sensing in real world and simulation means random sampling allows us to make powerful inferences about populations. Randomness is also crucial to performing experiments well. In real world, the sampling coverage distribution is either unknown or known by surveys. That means, especially if it's unknown, it's typically crowd population data, maybe towards big data. And the coverage is always much lower than 100%. So a sample is just a small snapshot of the entire population and should be representative. In surveys performed, for example, by social sciences, they have a plan to perform the experiments and they have already a model so they can make assumption about the distributions, the sample distribution, then they can plan the sample distributions. But they have distortions too. And especially in crowd population data, we have typically no known sample distribution. For example, with respect to the age of the persons, to the social level of the persons, the area they are living, and so on. In simulation, we have the opposite situation. Sampling has a 100% coverage. We can measure all agents. We can measure all entity in our entire simulation. And the sampling distribution is uniform or is known. No sampling and sensing error on the first glance. But simulation sensors depend on simulation model accuracy depending on real-world data. And now again, we have an issue. The simulation is wrong, but the sensing is correct. Here, the real world is of course correct, but the observations are distorted, and the sensing can be considered as giving us wrong results. This is shown here. Here on the left side, we have the real world with a large population. If we sample the population, we can only have a few small subset of the entire population, the sample, and only some of the entities are sampled, censored, and we have a sensor error, a measuring error that finally results in the sampling and the sensing. And we have a maybe known or unknown distribution over a spatial context, horizontal context, time context, age distribution, social parameters, and so on, or social classes. Here on the other side, we have some mapping of real-world humans, real-world entities on agents, for example, in agent-based simulation. And here we can probe each single agent. We have no measuring error, of course, and so the distribution is uniform and always known. We can cover 100% of the entire population. So then we have a data-driven approach, and that means model and simulation parameter P are typically based on experiments or data collected from the real world. That means population or survey data. Any bias and distortion of the measured data has an impact on the model and simulation parameter on the model accuracy. So we can perform an estimation of the parameter set. This is here just in the estimation of the unknown real parameter set of the entire distribution, and that means the estimation is the real parameter set that describes the entire population with an error, also just by a subset of the entire distribution. The point is a subset of D. And a parameter is a value that describes a characteristic of an entire population, such as the population mean not typically directly observable. And statistical models perform averaging of variance of observed in real world. So we have an oversimplification, suppression of important single events. This is one of my statements. We have to introduce variance in simulation to lower the gap between real world and simulation world. And finally, inferential statistics is highly affected by data bias, outlier, and sample distribution issues. Error accumulation, amplification occurs. So here we have an example. Simulation can be performed in different fields of application: social networking and crowds, pandemic outbreaks and disease monitoring. This is the example I show here. Economics. Here, these are typically cases that are strongly affected by the sample errors, by the sample bias, the distortion of the sample distribution, and or unknown sample distributions, and so on. Traffic and logistics are not so strongly affected by these issues. Not so bad as above cases. Typically in traffic and logistics, you can perform maybe a 100% coverage. I hope a logistics company know where they items are. Okay, in Germany, the parcel service mostly don't know where their packages are. Okay, this is a bad example, but typically in logistics and traffic too, we can reach nearly 100% coverage of the entire entity distribution. So here the worst case example, pandemic data. In pandemic situation, there's typically a domestic and centralized collection of infection cases. That means the population data. But this is not a typical sampling process. The observable can result from a mix of data sources. That means diagnostics of an infection, for example, by symptoms and with or without disease. That means indirect diagnosis. Diagnostics of an infection by laboratory tests, direct diagnosis with or without symptoms, disease, reason or cause of the test performed. Yeah, and finally, diagnostics of an infection by field test without any reason. So the observable depends on time, spatial, social, political and personal context. Calibration of population data is nearly impossible. That's my statement, my position. Maybe I'm wrong. But all what I have seen in the last 1.5 years about the simulation of the COVID-19 infection scenario were not very convincing with respect to this point. Here we see just a snapshot or a subset of the database, the German database with data infection cases collected by the Robert Koch Institute. And here you see at the beginning, here in the middle, and here more or less at the current situation. Here beginning, middle, and current situation over the years. Here the beginning of 2020, here more or less the mid of 2021. And what's important is here we have the weekly infection cases. We have no information about the cause of the test performed. The result, the person is tested positive on the virus. And so we have more or less totally unknown sample distributions over the age, for example. That means how many people were tested in a specific age range. Here we have the age range. Here in 5-year intervals from the youngest to the oldest peoples, to the elder people. And at the beginning, there were mostly infections detected by symptoms and by disease outbreaks. Then the test concentrated on elder people in some institutions, in hospitals, and in other institutions for elder people. And so we have a strong distortion of the distribution, sample distribution to the higher ages. Then, not the elder people were the cause of all evil. The younger people, kids and scholarly kids and so on, were the cause of relevance for all the situation that caused by the COVID pandemic. And so we have a strong shift to the lower age ranges. Then all people were tested. So maybe we have some uniform distribution in some meantime. But in the end, we have another issue. Vaccinated people were excluded from the monitoring because they are not tested anymore here in Germany. Here in this range, all people were tested. And here only the younger people were tested and only not vaccinated people were tested. So we have again a totally different distribution. And this is the main issue here with this population data. It's completely useless for modeling and simulation. So we need model calculation, very difficult for such kind of databases. But this means we need model calibration, simulation calibration, and sensor calibration. Here, the sensors are affected by measuring errors too. And we don't know the distribution over age and so on. So experimental data is needed to improve simulation. But experimental data is wrong. And so the simulation is wrong too. It's just here illustrated. Match experimental data with simulation to increase simulation quality. So we want to calibrate the outcome of the simulation with real-world data. But this is a difficult issue. So fusion of simulation and population data were already performed, for example here by Rainbow, calibration of a density-based model of urban morphogenesis. So we have a simulation model, we perform statistical validation, we have analytical studies that create a validated model, then we have population data, we have indicators, we have to compute indicators that mean aggregate variables, and we have real morphologies. And finally we compare it and make a fusion, and we hope we can create a calibrated model. But it still depends on errors on the population data, and the simulation model relies on real-world data too. So in the second step, auxiliary variables and statistical models distributions are required to calibrate population, crowd and survey data. So this is mean here we have to do model calibration, but we do have to do sensor calibration too. Here are two works by Changbo, a model calibration approach to using complete auxiliary information from survey data, and from Kim, calibration of a transit route choice model using revealed population data of smart card in a multi-model transit network. So digital data can be used too to create auxiliary variables and digital tracing, for example. Auxiliary variables and auxiliary models can be derived from real-world or simulation data, and analytical inaccessible variables and models can be approximated by machine learning. This is the field called surrogate modeling. But simulation and surrogate modeling relies again on real-world data. So surrogate modeling using machine learning can calibrate and validate agent-based simulations. Here's some examples by Lamperti, agent-based model calibration using machine learning surrogates, and by Zhang, validation and calibration of an agent-based model, a surrogate approach. But ML performs against statistical averaging. We lose individual entity-agent behavior affecting system observables. And digital twin methodologies introducing parameter variances derived from real-world data are required to increase simulation accuracy again. This is a contradictory goal, because the surrogate model performs an averaging, but digital twin methodologies spread the variance in the mean of an observable, for example. So here finally we have the surrogate modeling approach. Here shown, here we have population data, and of course we can perform machine learning, or we can apply machine learning to create an statistically averaged model to predict some system observables. That is the aim of the surrogate model. And here on the other side we have simulation, and with the sampling data we create, and of course here by different simulations run, we create another surrogate model predicting the desired system observables, for example, the development of infection cases and so on. And so the aim of surrogate modeling using machine learning is to map population data or simulation data, that means multi-agent data, and parameters on system observables. This is a complex task, error-prone. We have a mismatch again between real-world and simulation models. ML models are typically not transferable between real world and simulation. And yeah, is this correct? I'm not sure. My own experience and most results show that the models created here in simulation cannot be applied to sampled real world data. Of course they can apply it, but they give inaccurate prediction of system observables. We have a loss of individual variance by these statistical methods, and calibration is required again, both in simulation. The sensors here in real world, and the models that are created. So, to summarize, sensing of population data in real world is highly inaccurate, even if there are planned sample distributions like in surveys. Sensing in simulations is always accurate but not correct due to the simulation dependency on real world data, or the simulation model dependency, specifically the behavior models of entities. Calibration is a bidirectional process between real world and simulation data and is error prone too. Yeah, and finally, statistical models tend to average population behavior, suppressing individual entity behavior that can have important impact on system observables. Okay, discussions, questions, and comments are welcome. That's the aim of the expert panel. And of course, you can contact me here by my email and at the University of Bremen. Thank you for your attention, and I'm very interested in your comments and discussion and any questions regarding the field of simulation and surrogate modeling.